Hello everybody. In this video we are going to talk about the last part of this chapter, which is the energy balance for non-reactive systems. And this part is concerned with the properties of humid air. I believe this is not the right place to have this topic covered because it's covered in other courses like the mass transfer and it depends on uh, the way you can look at it. But I believe that the reason that this part is put in this chapter is because we can calculate the enthalpy of dry air. I mean of humid air. That's why this can fit in this chapter. Anyways, so this is an interesting topic, and it's a very uh, nice one. And the good thing about this topic is that it relates a lot to lot of phenomena that we see in our daily life. So that's why it makes it easy for us to understand and to grasp the concepts that we are going to cover here. So I would like to start with an introduction. This is what we are going to be covering in this video. And I believe this introduction is very important because it's going to give the important background information that we need to understand before we go ahead and see how we can do the calculations. So I would start with this image here. So this is a screenshot of the weather forecast or the display of the weather conditions from any application or on Google. You can find this shape that you can see, and I believe this is something that many of us, if not all of us, are familiar with. This is what you check almost every day to know how the weather would be like, if there is rain or not, if there is wind, what the temperature is, and this will show you, or based on this you will decide what kind of clothes that you're going to wear and to plan your day ahead. So there are a lot of things here. What I believe the most important thing that we look at is the temperature and the how the weather is. Is it sunny? Is it cloudy? Is it rainy? Then we would see here there is something that's called real feel, and which is another temperature. Sometimes it's higher, sometimes it's lower. Then there is the wind speed, how many kilometers per hour. You can find the humidity. There are things here that I think they're clear, and there are things that need clarification. For example, this dew point. What is this dew point? It's not clear. The real feel, why it's different from the actual temperature. This is something that we would be interested in. What is this humidity? How do we define it? This is something else that we will discuss. So let's start by giving the definitions of some of the parameters that we have. So there is something that's called the moisture content or absolute humidity. We give it the symbol HA. And it is so I think before we start, we all know that there is water vapor in the air, and this water vapor has percentage that would increase or decrease depending on the type of weather, and the humidity means how much water vapor is there in air. So we can describe it by two parameters. One of them is called the absolute humidity or the moisture content. In this case, we define this as the mass of water vapor to the mass of dry air. For example, if I have 1 kilogram of dry air, how much water is there? So it's the mass of water to the mass of dry air. So it's a ratio of mass to mass. There is something else. This is how we can define it. It's mass of water or divided by the mass of dry air. There is something else that we can or we see a lot, which is called the relative humidity, which is this. Sometimes it's just called humidity for simplification, but this is the relative humidity. So the relative humidity is the ratio between the partial pressure of water vapor in air to the saturation pressure of water. So there is something that we need to know, that there is a maximum concentration of water vapor in air that cannot be exceeded. The air can carry water vapor with an amount that cannot that it cannot hold more than this. This amount is called the saturation amount. Or since it's a gas phase, we can define the concentration as the partial pressure. So there is what we call the saturation pressure, which we discussed before, and we called it the vapor pressure. So they're both two names of the same thing. So the saturation pressure or the vapor pressure, it's the maximum partial pressure of water vapor in air. So when we define the relative humidity, we define it as the ratio between the actual partial pressure of water vapor in air to the maximum possible water vapor partial pressure in air. So this is how we define it: the partial pressure over the saturation pressure of water vapor. This is what we call the percentage of relative humidity. We have then the next, which is called the dew point. I would define, I just say the definition, but it requires some discussion, so I'm not going to go through the details now. It's the temperature at which humid air becomes saturated if it's cooled at constant pressure. We will come to this later. There is what's called the humid volume. It is the volume occupied by 1 kilogram of dry air plus the water vapor that accompanies it. So if you have humid air, then it's the volume of this humid air divided by the mass of the dry air. The dry air. Keep in mind that here we define it as the mass of the dry air. It's exactly like the denominator here. So let's talk about the dew point. Or no, not the dew point. There's something that we need to discuss first. So there's something, or we need to understand why dew happens in order to understand the dew point. So dew is a phenomenon that we all know. Okay, it's something that we see all the time, and this is something that you would see on the windshields and the windows of the cars, windows of the home. You can see it on the plant leaves. So this is something that happens, and it's very common to see this in cold weathers. If it's early in the morning, you'd see something like this. So why does this happen? So to understand this, I'll give an example, and then things would get clear. So let's say we have water vapor in air with partial pressure of 0.03. This is the partial pressure of water vapor, which is equal to the number of moles of water divided by the total number of moles of air. And let's say that this is under atmospheric conditions. So the partial pressure of air is the mole fraction multiplied by the total pressure, which is going to be 0.03 atmospheres. So this is the partial pressure of water in air. So again, I want to distinguish between two different things. The partial pressure is a parameter that we use to express the concentration, the amount of water vapor in air, or the concentration of water vapor in air. This is the partial pressure. It's the way of defining the concentration in the gas phase. And now we will. So the partial pressure, again, before I move on, because I know this sometimes it's a source of confusion. The partial pressure, as the equation tells, is a function of the mole fraction, which is the number of moles over the total number of moles, and the total pressure. It's independent on the temperature. Okay, so it is independent on the temperature. It's only dependent on the total pressure and the mole fraction. So to understand the dew point, let's compare three different times of the day. So let's say we have at noon or around noon, it's 11 a.m. where the sun is in the middle of the sky, the temperature is maximum. And then at 6 p.m. where the sun is setting and it's starting to get colder, and 4 in the morning where it's the coldest time of the day. So at let's say at 11 the temperature was 40 degrees Celsius, and at 40 degrees Celsius the partial or the vapor pressure is 0.0729 atmosphere. This is the vapor pressure, it's the saturation pressure, it is the physical property of water. So it is it's a property that we can calculate using Antoine equation. It is independent on the number of moles. It's independent on the total pressure. It's only dependent on the type of material or the compound that we are concerned with, and the temperature. Okay, so the parameters affecting the partial pressure are different from the parameters affecting the saturation pressure or the vapor pressure. So the vapor pressure equals 0.0729, which is larger than the partial pressure of water. So the relative humidity is the partial pressure over the saturation pressure, so it's 41.2%. The same day, where the same air containing the same amount of water with the same partial pressure of water vapor, the temperature decreases, so the partial pressure is not affected. What's affected is the saturation pressure, because the temperature decreases, so the saturation pressure decreases. So it's 0.0419, still larger than the partial pressure, so relative humidity is 71.7%. Now let's keep going, and this is now when things would get clearer why this happens early in the morning. So when the temperature decreases in the late at night, or at 4 a.m., the temperature decreases and the saturation pressure decreases. And now you would see that the saturation pressure is 0.023 while the partial pressure is 0.03. So the partial pressure is larger than the saturation pressure, which means that the relative humidity should be larger than 100%. And this never happens, because the maximum partial pressure of water and air is the saturation pressure. So air cannot hold water more than this partial pressure. So what happens is that the excess amount of water in air, which is the amount of water exceeding the saturation amount, will leave the air. So it will deposit from the air as small drops of water that deposit on any surface, like the windshield of the car, like the windows, like the plant leaves. So this is why dew happens, because air cannot bear the water anymore. It cannot hold all this amount of water, so it gets rid of some of the water in the air. So this is why the dew happens. So when we define the dew point, I'd like to go back to the definition. So the dew point is the temperature at which humid air becomes saturated if it's cooled at constant pressure. So if we go back to this slide here, so dew point, as we see, it gets closer to saturation, and at some point between 6 a.m. and 4 p.m. 6 p.m. and 4 a.m. it became saturated. So the temperature at which the partial pressure equals 0.03, or the saturation pressure equals the partial pressure, this is when, or this is the temperature that we call the dew point. Okay. So this is just to define the dew point. The amount of water vapor in air exceeds the maximum possible amount, air gets saturated, and excess water leaves the air in form of dew. So I hope this point is clear. There are two more terms that I want to discuss here, and these two terms are very important. One of them is called the wet bulb and the dry bulb, and the other is the dry bulb temperature. To understand the difference, let's understand what is the bulb. The bulb is the reservoir where the mercury is stored in the mercury thermometer, and we all understand how the mercury thermometer works. The temperature, the high temperature leads to the expansion of mercury, so mercury expands and goes more in this capillary tube, and you can see the temperature from here. If the temperature decreases, the mercury contracts, and then it retracts from the reservoir. So the temperature that we read on the thermometer is the temperature that we call the dry bulb temperature. This is in the normal condition. If you just hold the thermometer in air, the temperature it reads is called the dry bulb. It's called the dry bulb because the bulb is dry. There is no water here. It's a dry bulb from outside, of course. And now to understand what is the dry bulb temperature is the actual temperature that we read. So this is the temperature that the thermometer reads. We call it the wet bulb because the dry bulb, because there is another one that's called a wet bulb. So to distinguish between them, we call it a wet bulb and a dry bulb temperature. So now it's reading 75 degrees Fahrenheit. And now what is going on? This is a fan, of course, and in this video we are wrapping a small tissue that's wet with water around the thermometer bulb. So what is happening here is that this thermometer now, it is or the bulb is wet, so it's not dry as it used to be before. You might think, why we would do something like this, and would this affect the temperature? This is what we are gonna see now. So if we wrap this tissue around the bulb, what we are going to see here is that the temperature is decreasing. It was 75 or 76. It's now decreasing. Of course, it's sped up, but it's decreasing, and it keeps decreasing until it reaches around 74, 73 point something degrees Celsius. So this is what we call the wet bulb temperature. So this is a phenomena. This is a phenomena that we see. It's something that is a natural phenomenon. And the wet bulb temperature, it's the lowest temperature to which air can be cooled by evaporation of water into the air at constant pressure, which is what we see here. So this is something that describes or explains a lot of things. It explains why you feel cold when your clothes are wet, because the temperature of your body decreases because of this phenomenon. It explains why our bodies sweat. So this sweating is a natural cooling mechanism that our bodies do. This is because when you sweat, your body gets wet, and then it decreases the body temperature. And explains why if somebody has some fruits or vegetables, you can cover them with wet cloth. This will keep them fresh for longer time. This is because it's keeping them cold. It's decreasing their temperature, so it's keeping them cold. It decreases the rate of water evaporation, and so it keeps them fresh for longer time. So this is something that we see a lot. Now we want to understand some of one of the very, very interesting things about this. It's called the evaporative cooling phenomena. It's dependent on the same thing, the wet bulb temperature, that you can decrease the temperature of something by keeping it wet, and this is a very easy cooling mechanism. To understand the evaporative cooling, let's remember something, that people used to drink water before the refrigerators and all the cooling things that we are using now. They used to drink cold water from that's getting cooled by evaporative cooling, and this happens by putting water in clay pots. The clay pots are porous, so if you take a look at this clay pot, it's just a container that's filled with water, and if you take a look here, it's porous, so water can diffuse through the walls of the pot, and then the outer surface is wet. And this is something that you can easily see. You can, if you touch the pot, the clay pot that is filled with water, you will feel the water outside. So this water, it's now acting like the wet bulb. So this water wants to evaporate, and it will absorb the water, the heat from inside. So the heat that's absorbed by the water that is on the outer side of the bulb, it's cooling what is inside. So it absorbs the heat in order to take the latent heat that it needs to evaporate, and that's why this is what's cooling. It's cooling what is inside by evaporating what is outside. Again, that's why it's called evaporative cooling. When you keep it in a place where there is an airflow, this increases the rate of evaporation and the rate of cooling. So this is a very very interesting phenomena, and it's a very easy way of cooling things. There is a minimum temperature that this pot will reach, which is the wet bulb temperature. That's why it has a limit. It's not gonna cool it until it freezes. It's gonna cool it until its temperature reaches the wet bulb temperature. So this is all what I want to cover here. Next video, inshallah, we will talk about the calculations and how we can get all these parameters. So I'll see you then, inshallah. Goodbye.